Ladies and gentlemen, we ask that you please take your seats at this time as the program will begin momentarily.
When carrying out scientific research, we inevitably go through a cyclic process known as the science cycle. As the name indicates, this is a way to represent science as an ongoing process. In this lecture, I will take you through this process. If we look at the science cycle in more detail, we can see that it consists of 4 processes that connect the 4 main components of scientific research. The 4 processes are deduction, operationalization and investigation, data collection, and observation and induction. 4 main components are theories and laws, predictions and conjunctions, world reality, and facts and data. Let me take you through this cycle, starting at the top with the component theories and laws. What we mean by theories and laws can be natural laws or theories such as Newton's first law or the theory of relativity, but it can also be a behavioral theory. Basically, whatever is known about a particular phenomenon, such as concepts, principles, ideas and statements, gathered by other scientists before you. Be aware that in different fields, these theories take different forms. Theories may be exact in the natural sciences, but in social sciences it's common to have competing theories and varying perspectives and insights on the same topic. This is important to realize if you carry out multidisciplinary or even interdisciplinary research. These theories and laws form the framework for your research. When you're carrying out scientific research, you aim to add to the body of knowledge. What usually happens is that you make a new prediction, based on a certain theory or combinations of multiple theories. This process of making predictions by logically reasoning is called deduction and is the opposite of induction, which I'll come to in a minute. The next step is that we as scientists must start to investigate. In order to test our prediction, we must think how to operationalize this in an exact manner. What type of investigation is suitable and feasible? And is your investigation repeatable and reproducible by others? This is an important feature often overlooked in research. In order for people to accept your reported outcomes, other scientists must be able to check and verify your findings. Your study is often a sample, model or simulation of the reality, and it's important that samples, models and simulation are a good representation of such reality. Yet, at the same time, you must also make allowances. You will never be able to test everything and everyone, nor will your model of reality be a perfect match. It's therefore important that you also report these limitations of your study or experiment. Now that you've designed your study or experiment, you will start on your data collection. This process can have many different forms and shapes. These may include measurements such as failure stress or weight, but also measurements that are harder to objectively measure, such as how pilots experience their workload in the cockpit. This may differ depending on the pilot, the time of day, but also on how you measure workload. Self-perceptions of the pilot, observations by you. In this phase, you record data and observations, and you must be very careful not to add judgment to this phase if you want your research to remain as objective as possible. Also, be aware that you will inevitably always be somewhat subjective, even as a scientist. Each scientist views their research, and the way they do it through their own lens forms their own knowledge, experience and beliefs. There is no such thing as the naked or objective facts. The last step is to analyze your data and induce conclusions that may lead to new insight, theories and laws. And this is how science comes full circle. In the end, all theories and laws at one point in time were induced from observations. However, the process of induction is easier said than done. Induction is a process that is far more complicated than deduction. To generalize your findings is much harder and is often not possible from the limited data that you have. A famous, often used example of incorrect induction is this picture of an aircraft. This picture illustrates the work by Abraham Wald, a Columbia University statistician, who plotted all the bullet holes in returning bomber aircraft from a raid. From this data, the US military induced that all bullet-ridden areas should be reinforced to increase survivability. However, Wald noted that the plot was based only on aircraft that had survived their mission. He felt that an opposite conclusion could be induced from the same data. namely that the areas with the bullet holes were the areas where the bomber could actually take damage, and that the areas without bullet holes should be reinforced. He felt that those were likely the areas that when hit would cause the plane to go down. It's therefore very important to critically look at your data and your analysis of the data and explore if your induction to more general conclusions is justified and supported by the correct data, assumptions and analyses. This generic description of the science cycle is often reduced to a more practical linear format, that of the scientific method. This more linear representation of research argues that based on an observation, one asks oneself a question. From this, a hypothesis is formed. A hypothesis is a specific explanation or insight that can be put to the test based upon scientific expertise. Based on this, we select and design an experiment and carry out the experiment and collect the data. Now, it may be that the experiment doesn't work straight away and that you need to redesign your experiment before you can collect valid data. But once your experiment design is functional and the data is collected, it can then be analyzed. Based on the outcomes, the hypothesis is either accepted or rejected. If the hypothesis is accepted, we can draw conclusions and report our findings. If the hypothesis is rejected, it may be possible to see if we need to propose a new hypothesis or that at minimum we report our rejection of the hypothesis. It is namely a persistent myth that only successful research should be communicated. No, or the rejection of a hypothesis are also perfectly good scientific answers that add to the overall body of knowledge.